And electrostatics is another type of interaction that typically occurs between surfaces, especially when they're very close to each other in the nanoscale regime. And it's another piece of the puzzle that we need to consider when we consider the interactions among nanostructures. First, a couple announcements. I wanted to ask if there are any questions about the video assignment, if you've had the chance to read it online. I'll show you a little fun example video in a second. Okay, so I mean, as you read, the goal of the video assignment is to spend 5 minutes or less, shorter is fine, and describe a concept. And you can pick your concept. A few of you have signed up, but most of you have not signed up, so please sign up on the sheet. You know, we want it to be informative, creative, fun. I mean, it has to have both deep science content and perhaps some entertainment content. Basically, it has to be interesting and memorable. We'll grade you on the criteria that are listed in the assignment. So in the assignment, you saw that there are some links to websites that have short videos about nanoscience and nanotechnology. And you know, I was motivated to suggest this assignment because I think that video is becoming an easier and more portable and effective way to communicate concepts. And I bet that as some journals are now asking authors to have the option of submitting video abstracts in addition to a written abstract, that come 5 years from now, it'll be typical for when you write a paper to have a short video to accompany the paper, and maybe even some journals might require you to describe the methods of your experiment by putting up a video online and actually show someone how to do the experiment. I bet that'll definitely be true for journals that specifically publish methods, because communication of how you do something is really important for someone to repeat it. So a couple years ago, and I think they've done it twice, the American Chemical Society had this video contest called they called it the Nanotation Video Contest. And so some grad students at Berkeley put together this video, and I won't play all of it. But the request was to make a video that defines nanotechnology.
Miss Glory, what is nanotechnology?
Well, nano things are way too small for you or I to see. But soon the world will change because of nanotechnology. 1,000,000 nanometers that are lined up in a row are just about as long as a single flake of snow. Even germs are several thousand nanometers tall, so when you hear that something's nano, it's very, very small.
I think that is very interesting.
Well, I think that's very lame.
Poker monster. Miss Glory, why is smaller better?
Well, you see, big plastic tubes do not exactly have a great appeal, but nanotubes are stronger than the strongest piece of steel, and they're lighter than most metals, which makes them so ideal. And maybe later a space elevator may truly become real.
Ooh, a space elevator!
That's not possible.
Nano, 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 what a wonderful surprise. That ordinary is extraordinary when you make it nano size. Grains of sand do nothing when they're sitting on the shore, but nano sand glows brightly like no light has done before. They shine all sorts of colors, from red to green to blue, and they use much less energy than current light bulbs do.
Which is good for the environment, right?
That's right. Nano, 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 what a wonderful surprise.
Okay, so of course I don't expect you to do something like this, like have puppets and dance and sing, but that's the basic idea. And there are a lot of other examples, and there was a contest the next year, and I think some guys from a university maybe in North or South Carolina talked about solar cells, and they had more of a lab-type demonstration. They were in their clean room suits kind of dancing, talking about devices, holding up wafers, and stuff like that. You may not have props and so on, but I thought it was just a cool example of some people going really to the extreme to get this done, and this became really, really popular. Okay, and your homework is due next Monday, and I'll have office hours Wednesday, Mustafa has office hours Thursday, and he also has office hours on Sunday. So last time we talked about small-scale flows, and the idea is that the importance of friction grows as the scale of our problem goes down. It's in some ways no different than at a large scale, but we have to consider the boundary condition more carefully between the fluid and the wall. And we called this slip, or slip was our way of sort of quantifying or capturing the nature of the interactions between the molecule and the wall. And I'm sure you remember we have the parameter called the Knudsen number, which is the ratio of the mean free path, or the slip length, divided by the characteristic length scale of our problem. And the length scale that we talked a lot about was the pipe diameter. So comparing, say, the distance that gas molecules travel between collisions to the diameter of our pipe. And in the case of liquids, we defined what's called the slip length, and we related that to, for example, where the velocity gradient would be lead to a velocity of 0 kind of beneath the wall if you extended it by linearization. And we define that distance b as the slip length. Then in the case of no slip, the slip length is 0, and typically we have some finite slip. And if there were perfect slip, if there were absolutely no friction, or the molecules between the wall and the fluid didn't interact, you would have an infinite slip length. Yes?
Is the slip length a material property depending on the liquid and the wall material, or is it also dimensional?
So in general, we can say that it depends solely on the materials, but if you get down to really, really small sizes, then you can imagine that the dimensionality of the problem, the fact that you only have a small number of molecules, can affect the amount of slip. But in our cases, we, for example, can say it's just a material property. And this slip length was captured in an expression for the flow rate through a pipe, and our notation was that this was for incompressible but slip flow, and we had S equal to B for liquids, and S was related through an expression to the mean free path, which also took into account the amount of momentum transfer between the molecule and the wall. And here we saw that we could superimpose the case of slip upon the no-slip model. So this solution with S being very small, or this term going away, is our no-slip solution, and this is our slip solution. So you can see here, more or less, if our slip coefficient is on the order of the radius of our pipe, then slip becomes really important. If it's, say, less than 10% or 1% of the radius of the pipe, then it becomes less important. This term could be neglected. So things like atmospheric pressure gas flows at a scale of, say, a channel that's maybe tens to hundreds of microns, the slip length related to the mean free path would be very small, and then this term could be neglected. But when we get down to the micron and to the nanoscale, it becomes important. And we closed by kind of discussing what the molecular origin of slip is, and we won't get into these, many particular cases, but basically we just consider that the molecules in the fluid and the molecules in the wall feel each other, and this is determined by the interactions between them in the sense we could think of the same way we thought of van der Waals forces for some simple geometries, and also cases that the roughness of the surface might be important. So if the surface is rough, the effective contact between the fluid and the liquid, or the fluid and the gas, may be different than in the case if it was very smooth. And so now we'll talk about a couple examples of how folks have measured and observed slip flows. And it turns out measurements agree very well with the theory that we discussed for model objects at the micro scale. So this is a picture from the Archilic journal paper that you probably read already. This is a diagram of their setup that they use to characterize the flow through microchannels. And they designed, a lot of people have characterized the flow through microchannels, but they designed their system, including these two silicon wafers and their apparatus, so they could measure the difference between slip flow and no slip flow, or in other words, see if their measurements fit a model of slip flow or no slip flow for the dimensions. So they, for example, have two wafers. So these two silicon wafers are bonded to each other, and then they've etched some cavities in this bottom wafer that they call the channel wafer. And they're bringing the flow in the bottom and then through this kind of cavity from the back, and then it goes down this long channel, and then it comes out the right side. And they had to have fairly good control over their fabrication process. And they also made sure that they made long channels that were very, very shallow. So the length was important because they wanted to study the effect of compressibility. So they wanted to have a large pressure drop across the channel if they put enough flow through it. And then in order to be in the slip regime, they made the channels fairly short. So in this case, their nominal value of height was about 1.33 microns, and you can see they had very little variation. So they made sure they had a fairly uniform etch of their top surface layer here along the channel, and that let them use just the simple pipe models that we discussed, albeit adapted for a rectangular cross-section that's there to describe this behavior. And this is just a snapshot of their experimental setup, and they talk about this in detail in the paper. I think it's really impressive how they were able to measure such small flow rates. They measured flow rates equivalent to 0.1 thousandth of a cubic centimeter per second. And as a calibration, like if you're building a reactor to say, deposit a film or grow some nanotubes, and you buy commercially available mass flow controllers, pretty much the lowest range you can get is a few cubic centimeters per minute, or maybe an order of magnitude less than that. And it's very difficult to measure such small flows. And in fact, what they did is they had a setup where they didn't directly measure the flow rate, but they measured the pressure differential between two tanks. And so they had a reference tank and they had a flow tank. And it was important to make this method work that both tanks had to be held at the same temperature. So they were in a gigantic copper block that acted as a thermal reservoir, and they brought the tanks to equilibrium, and they made sure the gases were both at the same temperature, and then they opened this tank, and they use a very sensitive pressure gauge to measure the pressure difference between these two tanks as flow goes out of the flow tank and through their microchannel device here. And this is also all in an isolation chamber, so it's not sensitive to temperature changes. And this stuff down here lets them purge the system and also fill the tanks with the gases they need. So they related the pressure difference between the two tanks versus time to the flow rate through the system based on their knowledge of the geometry of the channels. And this is the plot of their results, or one of the results of one of their experiments. So this is the mass flow rate. So if you know the density of the gas and you know the pressure difference, you can calculate the mass flow rate. You know how much gas is being issued out of the tank per unit time. And this is as a function of the pressure ratio, which is, I think, the ratio of the inlet pressure of the channel to the outlet pressure. And the two curves here show the result for the slip flow model and the result for the no-slip model, which they calculated from the theory that we discussed, and it's in the paper. And this shows their data. And their data agrees very, very well with the model for slip flow through these channels. So it shows that not only is the expression we discussed and the approach we discussed very accurate, but it's also a validation that it's important to consider these effects for these sorts of geometries. And it turns out that, we talked about like differences in flow rate estimation or pressure drop estimation, depending on the conditions here, you're off by a few tens of percent, depending on which way you look at it, if you're trying to control a certain flow rate or control a certain pressure drop in this device. So I think it's just a nice validation and a really beautiful experiment that was able to show this behavior. Okay, so one more topic that I think is really interesting and is a nice application and demonstration of fluid flow effects now at the nanoscale. So now we're talking about dimensions of channels that are a few nanometers in diameter, and this pertains to study of flow through carbon nanotubes. So nanotubes are these long cylindrical molecules that are hollow, and model I had, and we talk about growth, we'll realize that they're typically capped. But by etching them open, you can cut them open, and if the nanotubes are grown well enough such that they are continuous, you can actually pass liquids and gases through the nanotubes. And starting maybe 5 or 7 years ago, some research groups started studying the flow characteristics through aligned films of nanotubes. And so what this group did is the gray piece here is a silicon wafer, and they grew a film of vertically aligned nanotubes a few microns high on this wafer, and then they filled the spaces between the nanotubes with the silicon nitride, just kind of a matrix to fill all the empty space, and then they opened up the nanotubes so they created a suspended membrane. So it's like taking imagine having a coffee filter over a hole in a plate and flowing through it, except now your coffee filter is the vertical nanotubes that are vertical pipes. And here's an SEM image of the nanotubes on the silicon substrate. And the silicon substrate is etched out, so you have a cavity that you can flow through. And I think that this is another example of their device where this hole here is meant to be the area that's open to the flow through the nanotubes. And then they were able to slice up their membrane and look at it in the TEM by cutting the nanotubes to be very, very thin. And this is a picture looking down of the individual pores. So these holes turn to these like so, and they used this method of looking from the top down to characterize the pore size distribution. So they had a size distribution of about, I think, an average pore size of about 2 nanometers. And what's been found by studying flow through nanotubes by this research and other research is there is indeed a very high flow rate, and a flow rate that's way faster than predicted by a conventional model, even a conventional slip model. And what this has to do with the fact that for example, for water, because the nanotubes are extremely hydrophobic, in simple terms, the water does not like the walls of the nanotubes, so it gets essentially repelled and pushed to the center. And that means that the amount of friction between the molecules and the nanotubes is very low. And so this is a plot comparing the permeability of the nanotubes, and here they're doing experiments both for air and for water, and it turns out that in addition to the hydrophobicity, because of the smoothness of the walls, there is also very low friction to a lot of things, although water is possibly an outstanding example of something that has extremely low friction. And the results here show, so the relative permeability of air and water in these units, you can just say this is sort of flow rate at a certain pressure condition. For 3 membranes they made, DW just means double-walled nanotubes because their nanotubes had 2 walls, relative to a control sample, which is a polycarbonate membrane that is typically used for filtration. And the reason why the nanotubes have such much higher flow rates, even though their pore sizes are way smaller than the commercial membrane, is because of the effects I described before, and also because the pores through the nanotube membrane are continuous and straight. And the polycarbonate membrane typically has kind of a tortuous network of pores. And then what they also did is they, by measurements of the average pore diameter and the number of nanotubes and the number of pores based on those TM images, which have some uncertainties, but you can say they're reasonably accurate, and the thickness of the membrane, they modeled the membrane as an array of parallel pipes, kind of like what I'm asking you to do on the first question in the problem set. And we're calculating, for example, this is an enhancement in the measured flow rate over a Knudsen model, and the Knudsen model refers to a free molecular flow regime. We didn't talk about that, but that's when the size of the channel is way smaller than the mean free path. And an enhancement over the no-slip condition. So this is basically the ratio of the flow rate through the nanotubes to the flow rate predicted by the no-slip model for water. And then they use that to calculate the effective slip length. And you can see there's a broad range here, but this is a pretty large slip length, a fraction of a micron in comparison to the tube diameter. So there is a lot of slip through these structures. And there was other work. This is just a table from a previous paper from 2005 that was studying flow through multi-walled nanotubes. And it's not really known how, say, if you take a nanotube membrane and you make it have, a diameter of 2, 3, 4, 5, 6, 7, 8, 9, 10, how the flow rate goes with diameter. It's just practically hard to do that. But this has been shown to apply for nanotubes of all diameters within the smaller size range of, say, 20 nanometers or less. So they tested a whole bunch of liquids and water and organic solvents and showed fairly high slip, and the highest slip was observed for water. And instead of saying, well, the enhancement over the no slip, these these researchers say showed their observed flow velocity and compared it to the effective flow velocity. And this is highlighted because this is the number I want you to use in the problem set. And note, as in the problem set, this should actually be in microns, not in millimeters. It's not quite so much slip, but it's still a lot. Like 54 microns is a huge slip length for such a small geometry. Okay. And one last example I just wanted to return to, we talked about the projector a while ago, the digital mirror display in relevance to the mechanical properties of these tethers that are single crystal nickel. And it turns out that because these mirrors move pretty fast, like they're not really moving a lot now, but if I were playing a video, the mirrors would be moving fast. And the behavior of the gas underneath these mirrors is pretty important. And I don't have data to show like sort of no slip versus slip, but you can just imagine if this is a pretty small gap, then the dynamics of the gas as it gets squeezed out and pulled in to the space under this plate is going to be important for the dynamic performance. So this is some data from Texas Instruments, the company that developed these devices originally. And what this plots is the amplitude of the mirror, or the mirror position, as a function of time, and this time is in microseconds. I guess they haven't labeled it, but that's a distance of about 10 microseconds at different gas pressures. And this is what they call their address pulse, which means basically the signal they're applying to the mirror to say move. Say I want to go from minus 10 degrees to plus 10 degrees. And this shows how the device responds. And you can see that the damping provided by the gas flow is really important. And they showed that by having different experiments done at different gas pressures. And at the limit of, say, 1 millimeter of mercury, or about a 1/1000th of an atmosphere, there's a lot of ringing in the performance. And you can see it takes a long time for the mirror to settle out. This wouldn't be suitable for video. But it turns out that at atmosphere, you get a pretty good dynamic response, and the mirror reaches its final position in a much shorter time frame. So now tens of microseconds. And if you're making video at a rate of, say, tens of hertz, then this is quite suitable for that, because you want the mirror to move over and be stable, so you don't see any jittering in the image and can update it frequently. So, so I would bet that they perhaps did these measurements, and it's probably a difficult geometry to model, but I'm sure there are considerations for the gas dynamics at these regimes. And also, if we're down at these pressures, then you can imagine the mean free path is quite high, and just by the fact that there are fewer gas molecules under the mirror to give it a cushion also makes a big difference. Okay, are there any more questions on the flow stuff?
For the flow through the double wall nanotubes or the multi-wall nanotubes, does it have is it only flow through the core of the nanotube, or is it the interstitial space also?
It's typically through the core of the nanotube. Now, if you think that think of graphite as carbon sheets packed as pretty much as tightly as they can be packed, then it would be difficult to get a molecule through. Like you can think of, in the practical case, some nanotubes are going to have defects. So maybe at some point there's a hole in the inner wall, and maybe a molecule can kind of get wedged in there. But in the ideal case, it's just straight through the center. Another thing is that if molecules are small enough, they can actually fit the other way, so fit kind of across the tube. So if you had a tube that didn't have that matrix material on it, and you had a really small gas atom like helium, I think could fit actually through the hexagons in the nanotubes. And there's been more recent work on graphene sheets, so single layers of graphene as membranes, where they actually pressurize one side of the graphene with a gas, and I think it's only helium, if I remember right, fits through the hexagons in the graphene, and the other gases, build up on one side and actually deform the sheet. Okay. So today, for the rest of today, we'll talk about electrostatics in solution, and basically the effect of surface charge. So if you have positive and negative charges on a surface, how those behave, how we model them, and how they relate to our considerations of interactions among nanostructures. And what we're going to get to is how this potential energy curve that initially showed for just interatomic attractive and repulsive forces effectively gets modified by the existence of electrostatic forces between objects. And this is perhaps the most basic way that we're going to consider stability of things in solution. So for example, nanoparticles that have some van der Waals attraction but have electrostatic repulsion. And also then this is going to relate very fundamentally to ways that we assemble particles. And if you have, for example, your van der Waals forces overwhelming the electrostatic forces, then your material will coagulate and you won't have a stable suspension. But if you have enough electrostatic repulsion, then it's possible to keep your particles stable in solution, and then, for example, deposit them on a surface or do some other things in the case of assembling a more ordered material. And we'll use some, just simple additive theory to add the attractive and repulsive interactions. And then, as we have time at the end, or maybe at the beginning of lecture on Wednesday, we'll talk about 2 examples in nanofluidic transistors and in electrophoresis. And maybe I should add that the flow through nanotubes papers and topic is one of the video assignments, as well as nanofluidic transistors are also one of the topics that's up for the video assignment. And that's also one of the readings today, Karnick's paper on nanofluidic transistors. And then there's a chapter or a section of a chapter that'll go through the theory that we're going to discuss today. And in the extras, there's a chapter from Israelishvili's book which discusses the same stuff that we're going to discuss from this reading today. I just provided it in case you wanted a slightly different perspective or wanted it, consistent with what the book that we had previously. But I liked how this was phrased and liked the content of this one better, so it's where I chose it. And then there's also a paper which is kind of interesting that talks about kind of the combination or the interaction between the Debye layer, which we'll learn about later, and slip flows, and basically how ions behave in the small region near a charged surface in the context of slip. And for example, how the ionic behavior changes whether you have a hydrophilic or a hydrophobic surface. And they also talk about how they do some really elegant measurements of the slip length on these charged surfaces. So it's a pretty in-depth topic, but it's a nice paper if this is a topic that you are more interested in. So the starting point for today is the fact that surfaces that are in solution become charged. So if you have a surface of metal, say a metal nanoparticle or a metal foil, or pretty much any other surface inside a liquid, then it turns out that there is an actual potential that you can associate with the surface, meaning we can basically assign a voltage associated with that surface. And this happens for a bunch of reasons, but mainly 2 reasons. And the first reason we're going to consider is that if you have molecules on the surface, those molecules will ionize. And for example, if you had a surface that had terminating carboxylic acid groups, then it's possible for this group to lose part of its structure, so lose, for example, a hydrogen, and then you'll have a negatively charged terminal group on the surface. Another possible way to accept charge, for example, happens in water solutions is absorption of ions from solution. So, if you have a bit of salt in water, then it's typical to have some ions come to the surface to absorb, and that'll result in some population of ions that are effectively stuck. And the geometry and the thickness of that layer where the ions are stuck is in some cases important, but we're basically just going to consider the case where you just have some charges at the surface and the surface adopts a surface charge, and therefore based on the charge per area we can assign it a surface potential. And this doesn't mean that there's energy flowing or anything, because of course the system has to be electrically neutral. And so what happens is when you have a charge on the surface and you have ions in solution, then the charges on the surface are balanced by the ions in solution. And if you were standing out in the middle of the liquid, far away from the walls, say this is a container and the walls are charged, and you looked around and you counted the number of positive ions and negative ions, they'd be moving around, but you'd have an equal number of positive and negative per unit volume. However, in the region of close to the surface, because you need to balance the surface charge, there is actually a distribution of positive and negative charge densities. And so overall, the system is electrically neutral. But for example, if you have a negatively charged surface, you end up with locally more positive ions here. They don't all go to the surface right away. It's not favorable for that to happen, but you have a decaying density of positive charge, and you have an increasing density of negative charge, and it all evens out. And what we're going to do is talk about this area where the charge density is changing, or the potential, the effective potential is changing, and that's what's called the double layer. And this is a picture of what I just described, that if you have a negatively charged surface, for example, this plots the ion concentration, or the number of ions of a particular type per unit volume. And far from the surface, so in the middle of the room, the concentrations are equal. So you have an equal concentration of counter ions and co-ions. Counter ions meaning if this is negative, counter ions are positive. So they're the black ones here. And the co-ions are negative. But near the surface, you have a much higher concentration of the counter ions, and you have a lower concentration of the co-ions. And then as you get far away, these concentrations taper out, and they balance. And if we can assign a surface potential to this surface, then we can calculate the effective potential decay as we go far away from the surface. So in the center of the room, the surface or the liquid is electrically neutral, so our potential or voltage is 0. And at the surface, our potential is as dictated by the number of charges. We'll talk a bit later about how this potential is quantified and measured, but now we're just going to assume that we have a surface with this charge on it. Okay, so we're going to sort of execute this concept or requirement of total electrical neutrality. And we're going to assume that we have a planar surface that is isolated, meaning it's far away from anything else that makes a difference, and it has a constant potential. And if we draw a little picture of our surface, like so, then we're going to measure our distance from the surface outward as x. And this is a kind of a picture of a surface and a graph together. And this is going to be the potential, which we're going to call psi, or the voltage. And we're going to say that the surface has a certain surface potential, psi naught, determined by basically the number of charges on the surface. And that as we go away from the surface, if you imagine you were a molecule and you swam over to the surface and you had a little voltage meter or a potential meter in your hand, and you swam away, the potential would decay out to 0 as you got farther and farther away. And we're going to call this the potential as a function of x. And our goal is to derive that function. So we can generally describe this by what's known as Poisson's equation, which is stated as such. We don't really need to know more about Poisson's equation at this point, but it says that the distribution, or the second derivative in 3 dimensions of the potential is equal to the negative of rho star, which we call the charge density, and this is in coulombs per unit volume, or coulombs per cubic meter. And in this 3-dimensional expression, it's a function of space, of x, y, and z. And then this is the permittivity, which is generally a measure of the material, in this case the fluid, to hold an electric field. So you've seen probably the permittivity of vacuum before, where the permittivity of a material E is what's called its relative permittivity times the permittivity of vacuum, which is just E sub naught. And that's a value of a constant. And so we're going to jump right away to saying, well, of course, we have a 1-dimensional problem here, so we can make our life a lot simpler. and we can just say that the second derivative of the potential psi in our x direction is equal to the charge density distribution x divided by epsilon. So also our charge density function is one-dimensional. And we'll say that our permittivity is a constant, a material property. And our boundary conditions are that the potential at the surface is our assigned surface potential, and that the potential at infinity, or far away from the surface, is equal to 0. So when, in a more practical sense, if we consider, say a beaker of solution, and we have say a metal strip in there, something we typically can get an idea of is we can get an idea of the concentration of ions in the solution. Like say you have deionized water and you take some sodium chloride, some salt, and you put in a certain amount of salt. You could say you can calculate how many ions you have per cubic meter of each the positive and the negative charges. And then by doing experiments, you could also get a measure of the surface potential. Not exactly the surface potential, but for now we'll say you can measure the surface potential. So now we want to relate this function to the surface potential and the concentration of the ions in solution. And we can say that the ions in solution obey what's called the Boltzmann distribution. And this tells us the probability of finding an ion at a potential psi. So it says that a quantity n sub I divided by n sub I at infinity is, and this is, say, number of ions per unit volume at a potential psi, as compared to the number of ions per unit volume in the bulk. So this is basically our concentration of ions in solution, is equal to an exponential function, which says it's less probable to find ions at a higher potential. And the exponential has a term like so, where psi is the surface potential, which we defined before. E is just the charge of an electron, and then Z is the valence of the ion. So for example, if it's sodium, C is 1. If it has 2 plus, then Z is equal to 2. And then KBT is just Boltzmann's constant times temperature, so it's the thermal energy. And from this relation, we can define the charge density. We said the charge density is just the total charge in coulombs per unit volume. So then our rho star is just equal to, for each particular ion, we can calculate a charge density, which is just the valence of the ion times the charge on the electron times n sub I. So now we have a function that relates the charge density to the expected distribution of potentials of the ions. And if we have multiple ions in solution, then we can just add the charge densities. And therefore, we can say that our rho star is equal to the sum over all the ions we have, which is equal to just the sum of ZIE times NI at infinity times our exponential function like so. So this says that, say we have sodium and chlorine, then we have two ions, and one is +1 and one is -1. And if we're far out, then the surface potential is 0 and the charge density is 0 because it balances. But if we're close to the surface, then we have an imbalance here, and we can calculate the net charge in the solution because this charge is accumulating in the solution to counteract our surface potential. And then this would just be, this is based on effectively our concentration in the bulk. And we'll define that in a more practical set of units in a little while. So what we can do is we can take this expression for the charge density and we can just substitute it back up into Poisson's equation, and then we have what's called the Poisson-Boltzmann equation, and we can solve it under some special conditions. So now we can write what's called the Poisson-Boltzmann equation, which says that the second derivative of the potential in solution, and if we collect like terms, we can bring out the charge on an electron, and we have the permittivity back from Poisson's equation. And we just have our sum over all the charges we have in solution. Times the exponential. And it turns out there's no general solution to this equation, but if we make some assumptions, we can get a solution that applies in a lot of practical cases. And the assumption that's typically made is that the surface potential is relatively low. And then you might say, well, how low? Well, it turns out that what's defined as a low surface potential is a case where the quantity of the valence of the ion, the charge on an electron, times the surface potential is less than the thermal energy. And this turns out to give kind of a rule of thumb at STP of 25.7 millivolts. So a surface potential of 25.7 millivolts is what's called a low surface potential. Effectively, the value of the thermal energy in terms of a potential at room temperature. And if we can assume that this term here is small, then we can expand our equation into a series, and then we can effectively linearize the equation so we have a solution that we can solve. So when this condition is true, we can then end up with a linearized equation that states that the second derivative of the potential is equal to a quantity E squared divided by epsilon kBt times the sum of the valences squared times the concentration far away multiplied by the surface potential. So this comes from expanding the relationship for the charge density into a series and then keeping only the first order terms and then substituting that back into the expression here. and it's described a bit more in the reading if you're interested in looking at it. And so now we'll define a quantity that we call kappa, where we'll say kappa squared is equal to basically the chunk of stuff we have up here, which is E squared divided by epsilon times the thermal energy times the sum of Zi squared and I infinity. And then our equation is simply the second derivative of x is equal to kappa squared times psi. And this has a simple solution if we solve it and we apply our boundary conditions, that the potential in solution is equal to our surface potential times e to the minus kappa x, or we can also say that the potential in solution is equal to the surface potential times e to the minus x divided by kappa minus 1. And this kappa is a really important parameter because that's what is called the Debye length. So kappa minus 1, so kappa has units of inverse length, and kappa minus 1 is what we call the Debye length, or sometimes it's called the Debye layer thickness. And it's typically reported in units of nanometers. So based on what we've just discussed, like, can someone tell us what this maybe practically means in terms of the way the surface potential behaves as you go away from the surface? Like, say, go ahead.
Wouldn't that be the length that you go from the wall at which there was a significant charge distribution?
Yeah. So basically, it's a characteristic length that says, how close to the wall is this effect of changing ion concentration important? Or in other words, if we're several Debye lengths away from the wall, then things are electrically neutral. If we're within a few Debye lengths or within a Debye length from the wall, then we're still seeing this decay of potential, and these electrostatic effects are important. So as you can imagine, if we think of electrostatic repulsion between two charged surfaces, there really isn't going to be an electrostatic repulsion unless the surfaces are separated by a separation that is, say, a few Debye lengths or less. And like in the case of, like a dynamic system or something decaying, it basically tells us the distance at which the potential gets to be 1 over E of the value of the initial potential. And this Debye length, this characteristic length, is used all over the place to quantify the distances over which these effects are important. So if we did a quick calculation of the value of kappa for a particular situation, by our definition of kappa, we could say, for example, at a certain temperature, we know kBT. If we have a certain solution liquid, we know its permittivity. And then if we have, say, sodium chloride, we know the charge on an electron, we know the valence of the ions, and we know the concentration in solution, so we could calculate kappa. So if we had, for example, say a beaker of sodium chloride at, say, a 0.1 molar concentration, and this means 0.1 mole per liter. And this could be sodium chloride, or it could be something like KOH, which goes into potassium and hydroxyl group. Then in this situation, if we ran our calculation, we would get that the Debye length is actually very short, so only a few nanometers. In this case, it's only 3 nanometers. And if we'll see in a minute the effect of change in concentration. So you might ask, well, what happens if we had a 1 molar solution instead of a 0.1 molar solution? Or what would happen if we had, say, a divalent ions instead of monovalent ions? And then the Debye length would change. But this basically says that these effects are important only very close to the surface. However, if you think back to the distances over which things like van der Waals forces were important, we're kind of in the same range here. We're in the what we call, a long range for intermolecular forces, the range of 1 to 100 nanometers. So these are generally playing in the same range and can be manipulated, so these electrostatic forces compete with surface forces. And for example, you have to do any kind of unit conversions. A possibly useful conversion is that the number of ions, say, in this would be ions per cubic meter per volume, would be equal to 1,000 times the molarity, which we define kind of like 0.1 mole per liter above, times N sub A, which is Avogadro's number. So basically saying the number of ions per cubic meter is just a conversion between liters and cubic meters. That's 1,000 times the number of moles per liter in your solution times the number of ions per mole, which is always the same, is always 6 times 10 to the 23rd. So then it could be substituted that kappa is equal to just this full quantity, 1,000 times the charge on electron squared times Avogadro's number divided by the thermal energy times the sum of our valences times the molarity, all to the square root. So if you wanted to calculate kappa and you are said, for example, here's the molarity of the solution, then you could just convert things like so. And if you have like sodium and chlorine, they both have a valence of 1. They have the same molarity. You have 0.1 molar of sodium, 0.1 molar of chlorine, so you just, add up. 1 squared is 1, so this is just like twice times the molarity. It's done that way because in some cases you might have something that dissociates into 2 ions, but one has a 2 charge, and then you have the other one with a 1 charge, and you have twice the monovalent ion as you do the divalent ion. So that lets you consider that, even though we might not run into any of those cases ourselves. Okay, so if we looked at the equations we just wrote out and tried to see how changing some parameters we may be able to play with would affect the kind of profile of potential in solution, we'd see something like this. So this is plotting the surface potential divided by, or the potential in solution divided by the surface potential. So at the surface, this value is 1, and far away it's 0. And in cases where we always have the same surface potential, this is showing the effect of varying on the left the concentration of the salt in solution, and on the right the valence of the ion. And what this is saying is that as you increase the concentration of salt in solution, the Debye length decreases, and the distance over which the decay in potential happens gets less. Who can tell us why that happens? Or give us maybe a physical explanation for why the Debye length is shorter in this case than in this case?
Because if you have more anions and cations, they press up against the walls more. So
well, yeah, pretty much. So if you have more ions available in solution, then there are more ions available to neutralize the surface potential. So if you have a certain surface potential, if there are more ions available, then the potential will decay more quickly. Same thing is at work here, only now we're considering not number of ions, but we're considering charge on the ions. So here you need like 1/3 as many ions with a charge of 3 to neutralize the same surface potential, and you can see that the decay increases. So in practice, for example, if you have a stable solution of particles, and you wanted it to coagulate. You wanted to let the van der Waals forces take over and kind of precipitate it out. One way to do that is to add more salt to the solution, so the effect of the electrostatic repulsion decreases, and the particles come together due to the van der Waals attractions. And through the reading, these aren't really important for us, but the reading talks about a number of solutions that exist for the Debye layer, and basically step back from that assumption we made that the surface potential is pretty low, and shows how the potential decays from a surface of an arbitrary system where you have a 0.01 molar solution of a 1-to-1 electrolyte, and compares, for example, what we did, which is what's called the Debye-Huckel approximation, to a more involved solution, an exact solution called the Gouy-Chapman solution, to, for example, the case if you had a really, really large surface potential and couldn't make that assumption that we did. And these kind of different solutions provide a kind of bracketing for the worst case and the best case in terms of the amount of potential you would have at a certain place in solution. But you can see that this Debye approximation is a pretty good result, and there's not a lot of variation among these. And this is the solution that we'll carry forward for all the calculations that we're going to do. And it's also possible, like we did for van der Waals forces, to solve the Poisson-Boltzmann equation for other geometries. And also, the reading goes through these cases of, like, basically what gave the different types of solutions on the previous plot. For example, if the Debye length is short, or the Debye length is large, or you have low potentials or high potentials, this is just a table showing the solutions for they're calling them microparticles and nanoparticles, but basically spheres. This is a case where you have small particles where the Debye length times the radius is small, and this is the case where you have large particles, or you have, for example, a low concentration, and the geometric consideration is different. But in each case, you can generally see, if we take the case of relatively low surface potentials and having small particles relative to the Debye length, then the solution looks fairly like what we had for a plane, except instead of our coordinate being x, we have our coordinate being r minus a, which is the distance from the center of the particle minus the radius of the particle. So we get a solution that's fairly similar to what we saw for the planar case. And they talk a bit about the solution for cylinders, which turns out to be expressed via Bessel functions, and so on. Okay, so the last major topic that's going to be important for us is to now think from this model of the potential distribution decaying from a surface, what the electrostatic force is. We now know the voltage is a function of position, so what repulsive force is that going to give us, which we can then equivalence, as I've been saying all along, to the attractive forces we know to be from van der Waals forces. So this is a picture from the chapter, and it shows a case where we now have two planar surfaces. And when I drew the first surface to derive the Debye approximation, I said that this one is uncoupled, and so nothing is within the range of the Debye length. And now we have another surface where the Debye lengths actually overlap. And you can imagine that in order for the surfaces to feel each other, the Debye lengths have to overlap. And so we're going to realize that there has to be a net force between these two plates to keep them at a static separation. And because of that interaction, we can do a little differential, and we can balance the force on a fluid element in the center here. So if, for example, we take an element of fluid in the middle of our two plates, where we have a surface potential that's equal on both plates and decays out from the sides, then we know that on the fluid in the center, we need to have a force balance. And we can say that this force balance is summed by a pressure force, which we'll call F sub x, which in the x direction, defined by moving away from the left-hand plate, is equal to minus the pressure gradient. So we're assuming we have a unit area here. And then we'll say that we have another force, which we're going to call the electric force or the electric field force. And by the definition of the charge density and the potential, we would get a resultant force that's equal to negative of the charge density rho star multiplied by the gradient in, or the first derivative in the potential. And so we can say that the force due to the pressure gradient plus the force due to the electrostatics is equal to 0. And therefore, we have that the pressure gradient plus our expression for the electric field force is equal to 0. And we can now plug in our one-dimensional Poisson's equation, which just introduces some more derivatives of the potential. And then if we write out the final result, we have one first derivative and then one second derivative of psi. And this being equal to 0. And we can take a look at this term here and just write it in a slightly different way. So this term here, the first derivative times the second derivative, is also equal to 1/2 times sorry. This would just be the first derivative of the first derivative squared. So if we took the first derivative of the first derivative squared, we would get 2 times the first derivative times the second derivative, and then that's why we have the 1/2 out here. So these are equivalent. And then we could combine this to write that now we have a first derivative of the quantity, the pressure, multiplied by the permittivity divided by 2 times d psi dx squared. And this is all equal to 0. And if this is equal to 0, then the term in the center here is equal to a constant. And the term here on the right, try green, is what's called the Maxwell pressure. And it's basically the contribution to the pressure from the electric field. And if our potential in solution is 0, then of course the derivative of the potential is 0, and we have no contribution due to the electric field. And then that also means that the pressure gradient in the fluid has to be equal to 0 because things have to have a force balance. But in the case here where the double layers are overlapping, this little element of fluid is going to feel a net force because of the difference in charge density on either side of it. And as a result, this is telling us there has to be a gradient in the fluid pressure. And then that means that that fluid pressure gradient is, in the end, supported by the plates and ends up transmitting a repulsive force from one plate to the other. And so to make this system stable, we would need to apply a force to each one. So if we went ahead with this solution, we made some assumptions. Like, for example, that the surface potentials from each surface alone were additive. For example, if you move these close, you could say that, like, over here there's a psi due to the first plate, and there's a psi due to the second plate, and the net psi is the psi from 1 plus the psi from 2. And we also, with that in mind, said that, you know, we aren't infinitely far away, but our separation is reasonably larger than the Debye length. We could write out the solution that tells us exactly what the repulsive force is. So if we have additive potentials and that H is greater than the Debye length, then if I flip ahead one slide, we could solve that the repulsive force is equal to 64 times the thermal energy times the concentration at infinity times a quantity big phi squared, which I'll define in a moment, times the exponential of minus kappa h. So the separation divided by the Debye length. So as the separation gets bigger, the repulsive force goes down. And our now unknown quantity is phi naught, which I'm going to call another quantity delta minus 1 divided by delta plus 1. And then delta is equal to the exponent of divided by 2 kBT. And this is for a 1-to-1 electrolyte. And incidentally, this is also seen in the Gouy-Chapman solution, that exact solution for the Debye layer. And because the Debye layers are interacting, we need to do this more exact approach. But with that and some more assumptions, we can come up with the expression like so. And now we can ask ourselves, well, you know, how does this force depend on something like the concentration of salt in solution, our molarity, and get a picture for why the force might change as you add more salt to the solution. So if we remember before, when we wrote out the expression for kappa, we could say that the inverse Debye length, or so I'm going to write it like this, kappa is proportional to the salt concentration to the minus 1/2, or you could say the Debye length is proportional to sorry, this should be minus 1. Then we can rewrite this as f sub r being, say, one constant times the salt concentration times the exponential function times the quantity like so. And as we change the salt concentration, this term will dominate. And basically tells us that as we increase the salt concentration, or the concentration of ions in the bulk, then our repulsive force will decrease. And this is, can be generalized not only for this case of two plates, but for other geometries as well. That you'll have a term inside the exponential that dominates over the term outside of the exponential as you increase the salt concentration. So, for example, what we have already is a force. And so if we want to go from a force to an energy, we can just integrate. So we could say that, the interaction energy, U, is equal to, some integral from zero interaction energy far away to some finite interaction energy U times du, which should be equal to the case where we have zero force at separation of infinity to the case of finite force of our repulsive force as a function of separation h dh. And now looking back at what's on the previous slide, that our equation for the force as a function of separation only has the separation h in the exponential. This is a pretty easy integral to do because we can just pull all the terms, including our special term here, out to the front. So it just says that we acquire another kappa in the expression for the interaction energy, and therefore we can write that the interaction energy U as a function of h is just the same expression as the force times another Debye length times the exponential. Minus h kappa. And then what we can do is we can say that the total interactions and interaction energy U total is equal to our electrostatic, so we'll call this electrostatic, plus our energy for van der Waals attraction. And we can look at the, sort of an equilibrium as where the total interaction energy, or the first derivative of it, as a function of d or h, depending on what parameter we're using for the separation, as being equal to 0. So now, without going through an example, we could take, for example, this expression for the electrostatic potential interaction energy for two plates and use the approximation which made an equivalence between plates and spheres that we derived in the van der Waals forces lecture to now, for example, calculate the net interaction between two spheres that have an electrostatic interaction and a van der Waals interaction. And you could just sum up the interaction energies and then look at the curve and calculate the first derivative, and that would determine for you, for example, the stability criterion. And this is the basic idea that if you have two particles in a solution, and for example, a case of two particles, if they are in proximity, then there is some overlap between the potential due to electrostatic repulsion and the potential due to attraction, and there might be some stable minimum here and a relatively large barrier to them coming into contact or coagulating that keeps them stable. this doesn't mean that every particle in solution has a specific separation, because they're moving around and there's diffusion and Brownian motion and so on, but it means that they are a stable suspension, and these interactions are preventing them from going very, very close together. And the probability of having two particles that have snapped in gets lower as the height of this energy barrier gets higher. So you want this energy barrier to be much higher than the thermal energy. So if we look in a bit more detail at what's going on here, you'll see that in different qualitative cases we'll have different curves. And there's more description of this in Israelishvili, the extra reading, if you want. But this is showing a net interaction energy curve as a function of separation if, for example, we added the van der Waals attraction, which was, and generally our 1 over r to the n expression, to the repulsive energy from the double layer. And if we added these two curves, we would get something that looked like we had on the previous slide, where you have this kind of potential well here, and you have an energy barrier like so. And in the terminology, this is what's called the primary minimum, so like way down here at the bottom. The peak is called an energy barrier, and this is called the secondary minimum. So if the system wants to seek the lowest energy, then the lowest energy is all the way here when the particles are together. But if you present enough of a barrier between the starting state and the primary minimum, then it's unfavorable for the system to approach this unless, for example, you actually push the particles close together. And the plot at the bottom shows what happens, for example, as we change the competition between these two types of interactions. So the top case, A, and the bottom case, E, are limiting cases. E being where you have van der Waals attraction and no electrostatic repulsion. For example, say no surface potential or very low surface potential. And the top case where you have, say, no van der Waals forces and electrostatic repulsion. And as, for example, you add more salt to the system, for example, to decrease the range of electrostatic repulsion, then you may go through a case where you have a stable minimum here with a relatively large barrier to coagulation, to aggregation, to a case where you effectively decrease the height of this energy barrier and make it favorable for the system to coagulate and for the particles to come together on their own. And the case here, E, of basically no electrostatic repulsion, where you can just ride the curve down into attraction, is really the limit. But the coagulation happens even before that, because once this energy barrier is fairly low and comparable to the thermal energy, then there's no hindrance to the system coming over that statistically and collapsing down to coagulation, where there's effectively no result due to the repulsion. And there, for example, this has been plotted out in another paper for gold nanoparticles, and you can see the kind of same behavior. In this case, we have an energy barrier divided by the thermal energy, and this gives more of a practical feel for it. So this parameter A is the radius of the particle. So these are small particles, kind of medium particles, and larger particles, 1 nanometer, 3 nanometers, 10 nanometers. And otherwise, all the parameters are the same. We have a surface potential of about 100 millivolts, and we have a salt concentration of 1 millimolar. And it's showing that the bigger particles are more stable because of the way the different energies scale. And this system would probably coagulate because the energy barrier is so slow, whereas this system has a very high barrier to coagulation, and in fact you can start to see a minimum out here.
Increase in interaction energy does not scale as same as surface separation. Or is it surface separation does not scale with the size of the particle? I mean, the peak of the surface separation is almost at the same point.
So sorry, you're saying as a function of the separation? Your question is why this doesn't scale more?
Why doesn't it shift?
Well, so this is the separation in each case. You're saying why doesn't it scale with the radius?
Right. I mean, the peak is almost at the same separation line.
Right.
Why doesn't it?
So it shouldn't necessarily scale with the radius. Like, you know, in basically, as the radius gets bigger, these become more like planes. And as they're smaller, they become more curved. And other than that, there's really little effect of the size on the electrostatics. So I don't know if I fully understand your question, but you wouldn't expect, for example, this peak to get farther because we're measuring the distance from the surface of the particles. What you're saying is this peak you're asking why this doesn't move out.
Yeah.
And
shouldn't charge, I mean, if you're increasing the size, the charge of the particle will also increase.
so, well, in this case, we're keeping the same surface potential. So you have the same quantity of charge per unit area. So maybe I could think of a clearer answer to your question, but this is, I mean, I guess just the way it scales. I don't see why it should move out if the particles get bigger or scale with the size. Okay, that's it for today, and we'll pick up on the examples when we start next time.